Okay, well, welcome to my YouTube channel. Never thought I'd say that one. But we're going to try and do feedback for exams using this kind of method. So I've got an example exam from Unit 8. We're going to go through for the feedback of this, and we'll go through question by question. I'll give you a bit of commentary on it, and you can see what the students written to get that 94%. So just missing 3 marks out of 50. So name one suitable application for each of these jointing methods. If we look at the dovetail joint, well, hopefully you know the dovetail joint is particularly good for drawers because it works on the principle that the front and the sides can't pull apart. Okay, so if you pull the front one way, it won't come away from the sides. Okay, traditional furniture would give you another mark. Drawers, cabinets, that kind of thing. Half lap joints, particularly good for frames and for doors. So that's a joint where in a corner it goes over the top of each other, sort of like that. Mortise and tenon joints, used for traditional building, construction, tables, chairs, frameworks, anything like that kind of thing. Okay, it's kind of not limited by the mark scheme, but it gives us some suggestions on what to put there. Okay, so table carcasses you can see in there. Which of the following does not require glue? Which joint? Well, a comb joint, sometimes called a finger joint. They are different technically. A comb joint looks like a comb, as opposed to a finger joint, which is the kind of square-shaped joint that you're thinking of, with a kind of abutments, if you like. Comb, literally more like a comb that kind of comes together, sort of like that slides together. Okay, as opposed to the finger joint. Dowel joint, where we've got dowels, obviously you need a bit of glue in that one. Mortise and tenon, again you need glue. Dovetail, the principle there being it's a self-holding one. You do need glue there to make it permanent, but it holds itself, it fastens, it doesn't come apart in one direction. Okay, so a dovetail joint there. Explain the purpose of the follower wheel on the router bit. So this is the router bit, and there's the follower wheel at the top with a bearing on. Okay, it's held together by a little screw. This is the cutting edge of the router. The bit that goes into the machine itself is here, so it's normally the other way up. But the follower wheel basically enables us to follow the work. I mean, it goes with the name. The mark scheme talks about the follower wheel is designed to run along the edge of a workpiece or a template or a jig. So it follows the edge, it's not going to cut into that jig because you want to use that again to ensure that the cutting blade stays a set distance from the workpiece. So either of those gets you a mark, so run along the edge and a set distance from the workpiece. The idea being that this little follower here, you can't cut into that because it's solid, it's not got a cutting edge, so it won't let your cutter go further into the workpiece. You can set that to where you want it to be. The follower wheel runs along the edge of a workpiece for 1 mark and can move freely to prevent burning. So often cheaper cutters like this will have nothing at the bottom here, and you can literally plough that into the work, and it sometimes burns or scorches the work, okay, your workpiece. So you can prevent burning with that kind of thing. Okay. I'll just turn over here. Slightly ambiguous kind of questions on this next one. So, question about wood joints forming a box. Label the 2 joints used to create the storage box. So, first one here, as you can see, a housing joint. So it houses the lid, it slides in and out of it. And then the next one, you can either have a comb or a finger joint. Shown in the picture, you can't really see it on this diagram, but it is actually a finger joint, what we term as a finger joint. Done by machine, brilliantly used by IKEA. Name a handheld machine that could have been used to create the groove around the top of the box. That would be a router. You could use a milling machine, you could use a CNC router, but it's going to be a handheld machine rather than a fixed machine, which is where the milling machine wouldn't have got the mark. The CNC router isn't a handheld one, so it's got to be a handheld router. The router is a handheld machine that you move around the work. The milling machine is fixed, and your workpiece moves around the work, or moves around the machine, should I say. Let me just shift it up. Explain 2 ways in which traditional handmade joining method used on a one-off prototype could be scaled up for mass production. So we've said here a jig could be used. If we look at the mark scheme, use of jigs for one mark to speed up manufacture, increase efficiency and reduce errors for another mark. So we've stated one thing and we've explained it with a kind of secondary point, if you like. It replaces a traditional joint with a knockdown fitting for one mark to make the joint easy to manufacture using CNC, or to make the furniture flat pack, which is more user friendly, for another mark. Use of machinery or power tools for one mark to speed up manufacture for another mark. So we're stating something and then we're explaining it. So when you see kind of 4 mark questions, you're looking at kind of 2 points that are explained well. Okay, you could give 4 individual points, but two points and then explain it would be better. One advantage of each of the following features on a wood screw. So the countersink allows it basically to be sat flush with the surface, and by flush I mean if we look at the surface there, the screw would sit flat, kind of like that. Okay, so it's flat or flush with the surface, it's not raised above the surface itself. Self-tapping, there's no need to drill a pilot hole or clearance hole. That's with the hole that the screw goes through. So when you're joining 2 bits of material together, I'm trying to get my hands right, like that. Okay, you'd have to have a hole through this one for a start. That is the width of the thread. Okay, so it goes through that one, it's not screwing into it, and it screws into this one, it bites into it and it pulls it forward back onto this one. If you didn't do that and it screwed onto both of them, it would just move up and down the threads. Okay, so you need a clearance hole or a pilot hole. That reduces the machining time for a second mark. Twin drive threads drives into the workpiece twice as fast, speeds up the manufacture. So it's got like an additional thread on it to kind of speed up the processing time, if you like. Next question then. So this question is about coach bolts. Describe one feature of a coach bolt that makes assembly easy. So what the mark scheme is looking for here is a square section below the domed head. It gives you 1 mark, so you can see that square section on here. Okay, embeds into the wood and stops the bolt from spinning during assembly. So it's kind of forced into the wooden piece and it kind of locks in place because it's not round, it's not going to spin round. It's going to lock in because it's square, and then you can tighten things up. So you get 1 mark for the domed head, embeds into the wood, stops it from spinning. The shaft of the bolt requires 1 clearance hole for 1 mark, which is easily machined with a drill. Okay, so you can speed it up by just drilling 1 hole, 1 size hole through it. Describe one feature of a coach bolt that makes disassembly difficult. Award 1 mark for a correct point and 1 mark for a relevant explanation. Okay, so same kind of thing again, 2 marks here. Coach bolts have a domed head, makes them difficult or impossible to remove from the head of the bolt. Okay, so you can't take that off. It's a domed head on it here, so it's got that curvature kind of like that. Yeah, and then your square section underneath it, and then it goes onto your round bit here. And you can't remove it, you can't cut that off because that's going to sit flat on the surface there. Okay, so you can't kind of cut away at it. Okay, which is what it's saying. Makes disassembly difficult. Number 8, just slide that up. Evaluate each of the 3 following holding methods used when turning on a wood lathe. Refer to appropriate examples as well as the benefits and limitations of each method to support your answer. Okay, so this is a 6 mark question. This is done in kind of mark bands, so 0 marks would be no response worthy of credit, so you've written either nothing or very little of any benefit whatsoever. 1 to 2 for a basic evaluation of listed points covering some of the factors, little or no justification. Okay, all the way up to 5 to 6 marks, which is where we should be. You can see I've given 6 marks here. A full and informed evaluation taking many fully explained factors into consideration. The discussion should be appropriately justified, showing an excellent awareness of all 3 of the different holding methods listed. So we've got to make sure that we're talking about all 3. And we're evaluating it, coming up with what might be the best, would be my way to finish it. Okay, so if I go down to what's called the indicative comments on the mark scheme. So faceplate basically can be used to shape and form bowls or domes. Workpiece can or will have hemispherical circular features. So going to be basically round. Okay, irregular shapes of pieces of wood can be fastened to the faceplate and allow a circular feature to be turned on its surface. So the idea of a lathe is we're turning things circular. Okay, so it's based around that. Screws must be used to fasten the workpiece, a secure method, but one of which can increase the risk of an accident if the screws accidentally hit with a chisel. So you can imagine we are, here's our faceplate looking from the side. We're going to make something like a bowl, so we're going to dome it off kind of like that. You're going to have to fasten it with some screws from the back. But if you were to kind of hit that with a chisel, okay, you can just about see my drawing, hit that line there with a chisel, then it would be causing a bit of a danger, a bit of a problem. Screw holes must be covered, filled or removed. So at the back, once we take that screw away, we've got to fill that hole to kind of make it less obvious. Turning between centres can be used to form spindles, so things like the top of your stairs, underneath the hand railing, the banister if you like, legs on chairs. Concentric profiles can be turned along the length of a piece of wood, so much like my pen, okay, you could hold it at one end and then between a centre at the other end, so it spins like that, big long piece. You could turn a nice long round piece to the same shape. You could put concentric circles, which are like lumps all the way down it, or various different shapes, various different kind of contours to it to give it some kind of elegant shape. Chuck allows for a wood piece to be held without a need for screws or support from the tailstock. The tailstock's the bit where we're holding it at one end, sticks out, and the tailstock kind of pushes in where the drill bit goes. Okay, that's the machine that kind of holds it in the other end. Okay, so you don't need that with a chuck. Also suited to bowl manufacture and objects where the intrusion of a screw hole in the product might prove unsightly. Size of the workpiece is restricted by size of some chucks. So depending on how big that chuck, that holding device is, depends on what you can make. Also the distance between the chuck bottom and the bed of the machine also dictates on how big that thing is. So again, if you look at my diagram, the bed of the machine would be kind of down here. So you can only make something with that kind of distance here in mind. Okay, just about see that. Okay. So it depends on the size of that, the size of the chuck, there to there again, and the size from the centre to the edge of the machine. Okay. If we look at our maths question now. So when steam bending, timber, 1 hour of steaming is recommended for every 25 millimetres of thickness. Calculate how long a 4 millimetre thick workpiece would need in the steam box. Show your workings and round to the nearest whole minutes, making sure we're doing that. So we've divided 25 millimetres by 4, gives us 6.25 for what we're talking about, 6.25 minutes per millimetre. We're going to multiply 60 by that. Excuse me, 60 lots of that to find out how many in an hour we've got. So divide 60 by 6.25 gives us 9.6 minutes, and then round it up to equal 10 minutes. Okay, so a little bit of maths there, making sure that we've got the answer to the right bit where it says round to the nearest whole minutes, making sure we've answered that bit. And you can see we've got all our working out going on here, and its answer is clearly shown at 10 minutes there. Okay, so the image below shows a Paimio chair designed by Alvar Aalto, 1932, which features a framework and seat made from laminate birch. And again, this is on that graded scale from 0 being nothing there, all the way up to 5 to 6 marks of full and informed evaluation, taking many fully explained advantages and disadvantages into consideration. Discussion should appropriately justify an excellent understanding of the lamination process. So if we look at advantages, formers used to replicate the chair frame, speeding up the production time. So we're going to make a former, we're going to bend that stuff around that former to speed up the processing time. Okay, we're not just bending it haphazardly. Allows for more curved forms to be incorporated in design, removing constraints and limitations of traditional woodworking techniques. So we're not dealing with just straight furniture now, we're making these elegant curved shapes that we can have. Forms can be reused many times if they're well made. Okay, so the better we make them, the more often we could use them. Likewise, if you're only making one, you might just nail something together, whereas if you're going to do it lots and lots of times, you'd spend some time making it well. Use of adhesives or alternating layers of ply creates strong frameworks which have some flexibility. So we're layering it up in thin layers, which allows it to flex a little bit. You can use vacuum bags. Only one half the former needs to be made. Expensive veneers can be used on the outer layers. That one about the one half of the veneers. If you imagine this kind of main bit of the body here, you could kind of cut the negative out, the bit that's underneath it, put it in a vacuum bag and suck it around that shape. Whereas if you're going to make the kind of positive side of it, we've got the negative underneath here and the positive, the male bit that's sticking into the female bit. You'd have to use a massive another lump of material, lots of clamps, etc. A vacuum bag is literally a bag that you suck the air out of. Expensive veneers can be used on the outer layers to give a high-end finish while keeping costs of internal ply layers low. Okay, so you could alternate that, have nice stuff on the outside. Choice of hardwood or softwood veneers, flexi-ply, aero-ply for internal layers, which means different materials can be used for different characteristics and budgets. Use of renewable materials, less restricted by knots and faults in the timber compared to steam bending or more traditional woodworking methods. So it doesn't really matter if you've got knots and things like that. The raw material, the veneers or flexible plywood, is cheaper than using solid timber. Disadvantages then, formers need to be accurate and robust. The manufacture of formers can be costly and time consuming, so we split it up for starting to advantages and disadvantages. Cure time, so how long it takes for the glue to set on the adhesives, can slow down the manufacture. Forms can often only be bent significantly in one direction due to the structure of the grain. So you can't really bend it across the grain, otherwise it's likely to break. Laminates must be formed with excess material, which is then machined away. It's wasteful. Okay, so you've got to allow it to slip a little bit so you can clean it up afterwards. And adhesives can make recycling and reuse of waste very difficult because you've got to separate those up. Okay, so again, a bit of a judgment call here. So, we've lost 1 mark here. Just in my opinion, we're just not quite saying as much as I want to, and I'm really pushing this student to kind of get as much down as we can. What we've got down here is fantastic. I'm just trying to kind of push a little bit further. Let's flick over. The image below shows a child's wooden stacking toy designed to develop hand-to-eye coordination in babies and toddlers. I suggest 2 suitable joining methods to attach the pegs to the base. So we could use a dowel joint, which is literally going to be like a little peg through the bottom of that into the base. A butt joint reinforced with wood screws, so it literally could be, there's the base. Okay, there's more to go on there. We've got our uprights here, so let's draw 2 for you. The first one could have a dowel, pin it into the base. The other one could just have a hole. We're going to put a screw through from the bottom up into the top. Okay, so either way you've got a butt joint, which is that where it just butts up to it, sits flat, and we put a screw in, or in this one we've got a dowel sitting in it. Probably a little bit more robust, a bit more attractive because you can't see a hole for it. Suggest 1 suitable finish and 1 application method for this mass-produced product. Finish, we're looking for a non-toxic water-based paint, toy-safe water-based paint, something like that. Basically, you can't have anything that's going to have some toxicity to it because kids are going to put it in their mouth. Okay, it's a key one. It's a child's toy, so you know straight away it's going to have to be some kind of stain or some water-based paint, not a solvent-based paint. How is it going to be applied? Well, chances are they're going to spray it on. Okay, so there's your 2 marks. So naming 1 finish and naming the application. So how is it going to be put on? Next question then, about pressure treated timbers. This is another tricky one, and again I've been a bit critical on here. It's really well answered this, but I'm just trying to push again, like I say. So describe the process of pressure treating wood. So we're looking for the timbers placed in a sealed chamber. Vacuum removes wood from the timber on a cellular level. Preservative solution is released into the chamber and hydraulic pressure is applied for the preservative deep into the timber. Okay, so it forces it under hydraulic pressure, so you're using that liquid pressure, pushing it into the timber. The second vacuum extracts excess preservative, which is pumped to a storage container for reuse. So we force it in, anything that spills out gets sucked away and is reused. The low pressure inside the timber draws the preservative further into the timber. Timber is removed from the chamber, left to dry. So it's 1 mark for each correctly described step, up to a maximum of 6 marks there. Okay, so we're looking for 6 statements. And one disadvantage of using pressure treated wood, so we're looking for the copper-based treatment solution is toxic, can be bad for health or for the environment, 1 mark for each of those. Any cuts made after the treatment process require further treatment, 1 mark, which is time consuming, 1 mark. Okay, so again, on that one, you're looking for a statement and justifying it really. Okay, one disadvantage of using pressure treated wood, 1 mark for a correct point, 1 mark for a relevant explanation. Okay, so there's your total 50 marks. Quite a nice exam, some technical bits on there to kind of keep us going, but hopefully that's helped us with a starter. I'll try and do another one as soon as I can. I look forward to it. Like it, subscribe, whatever you have to do. Thanks, bye.